I think the recording is on, and um, let's address these topics now. So, as the scientists suggest, we are going to be talking about switches. Um, we will relate them to logic gates, and really, if we look at the internals of logic gates, we are going to see how we can build those gates, or at least the functionality of those gates using transistors. So, a switch, and you see a switch several times every day. A switch is simply used to connect or disconnect 2 points. So in this particular diagram, we have A and B as two endpoints, and in the middle there is a switch, a toggle switch, a push button switch, a slide switch, whatever you may have. And that red arrow over here indicates that you could have that switch be open, in which case A and B would be disconnected and no current can flow between A and B. Or the switch could be closed, which means that the arrow is pointing down, indicating that it actually connects to the other uh, end. And when it happens, the switch is considered to be closed, and now we have a connection between A and B, current can flow. So those are going to be the two switching states. Switch is on, meaning A and B are connected. Switch is closed, sorry, so switch is open. Open means disconnected. You could also use off to say the same thing. And in the other case, switch is closed is when they are connected, or you could say switch is on. So that's how you are going to draw it in a schematic, a switch in a schematic. Now, mainly we will be looking at mechanical switches and electronic switches. So a mechanical switch could be a relay, uh, could be something as you see over here, somebody turning it on and off. But this process actually needs someone to stand there and turn things on and off. So it's a manual switch. An electronic switch is when you have a electrical signal controlling the switch, the switching behavior from low to high and high to low. And we do that in order to make that switching happen very, very fast. So instead of somebody standing there and turning it on and off, which could be very, very slow, now we can do that switching very, very fast by using a high frequency control signal to control the base of the transistor. Transistors are generally in two types. There's a bipolar junction transistor, BJT. This is the type that we are in fact using in our class. There are other types of high speed transistors called MOSFETs, which stands for metal oxide semiconductor field effect transistor. We are not going to be using this for our class, but the operations are very similar. The underlying principles are very similar to a BJT. The names of the terminals differ a little bit. For a MOSFET, instead of having an emitter base collector, we have a source base and a drain, source gate and a drain. So the names of the terminals are different, but their usage is very similar. But the advantage with a MOSFET is that they can be smaller and faster compared to BJTs. So that's a quick background on switches and where you might see them. Um, Now, we are going to try to relate all these topics with each other as we go through the lecture today. So the first thing that we'll try to do is we'll try to build or analyze, in this case, a circuit model of an identity function. So what is an identity function? Well, simply the output equals the input. So that's identity. Or you might also call this behavior a buffer. So no change logically. So it's not like we are inverting the input. Remember, we are talking about switching states in the two extremes when the switch is on and off. So we are looking at input either being low or high, output being either low or high. So when both the states of the input and the output are the same, that's called an identity function. Y equals X, output equals input. So let's see how we can build this function using a circuit. For this, we need a voltage source, an actual switch with that toggling between the open and the closed positions, and say we have a light that could potentially turn on and off. So we are going to represent the position of the switch by using a variable. In this case, it's going to be a binary variable which can hold low or high value or open or closed value. That's X. And we have the light, and it could be off or it could be on, and we are going to represent that state of the light as Y. So either on or off. And let's say that light is we are using RL as the resistance of that light. We have a voltage source Vs. Now, clearly, when the switch is open, that means there is a disconnect here. When the switch is open, no current is going to flow in the circuit. Is is going to be zero, which means that the light is going to be turned off. And when I close this switch, now I have a closed loop. The current is going to flow, and it is going to be Vs divided by RL depending on Ohm's law, and now the light bulb can turn on. So we have got the two extreme cases over here when the switch is open and closed, and how it affects the output Y or the light bulb. And as you can see, if I were to map these states open and closed to a 0 or a 1, as such, open means disconnected, low, 0, and closed is connected, high, 1. And I similarly map the state of the light bulb from off is 0 and on is 1. So by using this mapping, I can translate a table like this, which has words and quantities, into a table that looks like this. So over here, X is representing the state of the switch, Y is representing the state of the light bulb, and when the switch was open, the light bulb was off. When the switch was closed, the light bulb was on. So here we have the binary input, and over here we have the binary output, and it is binary because we have only two states, 0 and 1. And as you can see, the input is exactly the same as the output. So that's an identity function, and this table is called a truth table. A truth table uh, includes or should include all the possible uh, binary levels of each input. So in this case, you only have one input, so there will be two rows in this table. Now using the truth table, we can map this to a logic expression. In this case, y equals x. So the logic expression is going to be y equals x. And we can sketch that into a schematic using a triangle. So a triangle represents a buffer where we are not changing the state of the output. We are just taking the input and providing it at the output. So binary input goes in, binary output comes out, just a triangle which represents a buffer. It is not changing anything. Okay, changing anything, there are some underlying issues with not with saying not changing anything. We do have a usage of buffer. We will see that a little bit later. Why do we ever need to use a buffer? All right, so that's a identity function. Now, by playing with the position of this switch, we can design or model several other logic functions. Let's try to see how we can do that. Uh, by the way, we have been talking about 0 and 1 being input and output, but those low and high levels need to be associated with a certain range of voltages. And for complementary MOS technology, CMOS technology, uh, that's a technology that is used to design the transistors and the logic gates using those transistors. Low or zero, logic zero, is a voltage that is between 0 and 1.5 volts. So any voltage in this range is going to be considered to be a low state. And as you can see, um, if it is very close to 0 volts, then it is essentially a strong zero, meaning there's no confusion about whether it is a low or a high. And as it gets close to that other edge of the range, the low state actually is becoming a weak zero, because now there could potentially be a confusion if it is 1.5, is it a zero or not? So it's becoming a weak zero. On the other hand, we have a high state. The range of voltages that represent the high state for CMOS are from 3.5 volts all the way to 5 volts. So that's corresponding to logic 1 or true. Now over here, the story is a little bit reverse. 5 volts is actually a strong one, but 3.5 is going to be a weak one. Very similar reasoning to the same the low. So if it is 5 volts, then there is no confusion whether it is high or not. But if it is 3.5, then there could potentially be some confusion about that state. Now, the obvious question here is, what about the voltages that are between 1.5 and 3.5 volts? Well, those are undefined voltages. So if a particular signal is, say, 2 volts, then it is neither low or nor high in the case of CMOS circuits. All right, let's move on to the next logic function. We have a NOT gate. So hopefully this goes a little bit faster. Um, we have changed the location of the switch from before. We have placed a resistor RS. Light remains as is. We still have the DC voltage source, and we have a table over here that monitors the state of switch I1, which is the current through the switch, I2, which is the current through light, and the state of the light bulb. We are still using X to represent the state of the switch, Y to represent the state of the light bulb. When the switch is open, no current can flow through the switch, which means I1 is 0. So that means that all the current from the voltage source has to flow through the light bulb, which is I2. In this case, it would be Vs divided by the sum of those two resistors, Rs divided by RL. And in this case, the light bulb is turned on. In the other case, when the switch is closed, then all the current from the source is going to flow through the switch. None of it is going to flow through the light bulb because we have RL present. So when current is going to take the path of least resistance here, the I2 is going to turn out to be 0, but I1 is going to be Vs divided by Rs. And if there's no light flow, there's no current flowing through the light bulb, it's going to be off. Now, if we use the same mapping as we used before, open translates to 0, closed translates to 1, on translates to 1, off translates to 0. We have a truth table of the NOT function, which is also called an inverter. Over here, truth table of an inverter. So essentially we have a flipping of the state, getting complemented, getting inverted. So it can be represented using a logic expression by saying y equals x complement. So the bar over that x represents an inversion operation. Uh, In some places, you might see the terminology as not of x or x prime. They all mean that x is getting inverted. So the input gets inverted to for you to be able to express the output y. How do we sketch it? Binary input x goes into the logic gate. We still have a buffer, but that bubble actually signifies inversion. So that in in total, that's a NOT gate that you have been seeing in experiment 6 so far. And we have the binary output at the right side of that gate. How many inputs can a NOT gate have? It is going to be only one. How many outputs can a NOT gate have? Only one. So it's a one input, one output logic gate. Both the buffer and the NOT gate have one input and one output. So what happens if we need more than one? Well, we simply are going to look at uh, we are going to try to pack a lot of NOT gates into one IC in that case. So if you can see figure C-1 on experiment 6, right up, this particular chip has 6 inverters in one chip. They are all performing the same operation. Input is a low, output is a high, input is a high, output is a low. But this NOT gate is based on Schmidt trigger, meaning two thresholds. So there is some tolerance to noise, but it could also be a comparator based inverter where there's no tolerance to noise and there's only one threshold level. All right. So that's a quick discussion on NOT gate and the identity function. Um, Now let's kind of talk about uh, a very useful concept here. So we have, say, let's go back to our two students, student X, and then we have student Y approach here. So student X says, if you have, um, say, design one, or I should say, system one, and you need to connect the output of system one to, say, system two. And the output over here is of a binary nature, low or high, and we need to connect that to the input of system 2, and we have that same situation, the same requirement from student 1. Okay. So let's say the student X uses this approach. So that's our design issue. Connect the output of system 1 to the input of system 2, and we are assuming that the signals that are being used here are binary, low or high. So student X approach is very simple. So student X says, you know what, because the output of system 1 just needs to equal system 2, I'm just going to connect them by a wire. So just by using a wire, student X connects them together. But student Y actually connects them using a buffer. A buffer, there's uh, nothing as a buffer. It's actually a combination of two gates. But a buffer is essentially two NOT gates back to back. So the logic level at the input gets flipped once, flipped twice, and that's essentially our buffer. So we are representing that as a buffer, but in reality, it is a series of two NOT gates that goes in there. So student Y approach is using two NOT gates or a buffer. Student X approach is just by connecting a wire. Well, who is going to be right? Are they both going to be right or not? They are both going to be right only under ideal conditions, meaning that we have very strong output over here. And we talked about what a strong 0 or a strong 1 means. If it is a strong 0, it's a 0 volts or 5 volts in the case of high. In that case, the translation of that input to, the output to the input here is going to work out okay. And also over here. However, if the output over here is weak, then we may end up in trouble, because if there is some sort of resistance of the wire and it is a weak 0 or a weak 1 that is the output of system 1, then system 2 might not get enough or the correct voltages that represent low and high. So that could be a big problem here. Student Y approaches use a buffer. So what does a buffer do in the case of weak 0 and weak 1? It will actually translate that weak 0 or weak 1 into a strong 0 and a strong 1. So by doing that, we are not going to have that problem. So student Y approach applies for all cases. Student X approach will work only in the define what is right. Uh, I'm not sure, Joseph. I'm not sure when I mentioned right. Um, if I said right approach, I meant a correct approach. So student X approach is going to be a correct solution only under ideal circumstances when we have a strong 0 or 1. But student Y's approach is going to work for even the worst case, where we have weak binary signals present at the output of system 1. So that's essentially the use of buffer. So even if it doesn't do anything, y equals x, it is still able to give us this usefulness. So we can use this to as a bridging between why the second can change the weak to the strong. So this weak into a strong, we are going to see that when we look at what is inside. So that question will be answered when you look inside the buffer. So just hang on to that question. Right now just assume that it does that. Um, it has to do with what is inside, and we'll address that in a few minutes. All right. Let us talk about an AND function. Both switches have to be closed in order for light to turn on. And AND functionality, you need the switches in series. So you need switches in series. Keyword here is series in order for the light to turn on. So over here we are representing x1 and x2 as the state of the switches. Y is representing the state of the light bulb. We still have a voltage source. That's our circuit model of AND function. AND is a logic gate, the symbol of which is a big D. X1 and x2 are inputs, Y is the output. The logic expression of an AND function simply has a dot in the middle of the binary inputs. So y equals x1 and x2, written as this or simply as that. So the condition over here is only when both the switches are on, meaning in the closed position, current can flow and the light will turn on. If one of them, either one of them is open or both of them are open, then the light will be off because the circuit is not complete and current cannot flow. So that translates into a truth table that looks like this. You have x1 here, x2 here, and because we have two binary inputs, we are going to have four possible entries in the truth table. This is number of inputs, and this is 2 because it's binary inputs. So we are going to have four rows, 0, 0. So four different possible combinations between the state of x1 and x2. And only when both the distinguishing entry in this is only when the switches are both closed, this and this, only then the output is 1, which means the light can turn on. Notice over here, as the size of the truth table increases, so to maybe 3 inputs and 4 inputs and 5 inputs and so on, we would need some sort of a pattern, some sort of a systematic approach to fill in all these combinations. And the way we do that is by taking the rightmost input, which is the least significant input, and flip it or toggle it every time. So it goes 0, 1, 0, 1, 0, 1, 0, 1, and so on. For the next higher level, in this case x1, we go two zeros, two ones, two zeros, two ones. And if we had more, we would go four zeros, four ones, four zeros, four ones, followed by eight zeros, eight ones, eight zeros, eight ones, followed by 16 zeros, 16 ones, and so on. So it's going to, those number of zeros are going to increase in powers of 2. So that's a very neat trick if you want to look at a really big size truth tables. Okay, so we talked about the truth table, we talked about the logic expression for AND, we talked about the symbol, and also note that we could have a 3-input AND gate over here. 3-input AND gate would simply mean that we have an additional switch in series in the circuit. So the one thing that I would ideally have you guys retain here is the thing that I have highlighted. For AND, we have switches in series, so one after the other. So the same current flows through both the switches. All right, let's try to move on to an OR function. In this case, we have two switches that are going to be in parallel. Things are now going to sort of appear in complementary fashion: series and parallel, and an OR, buffer and NOT, low and high state. So almost everything is going to be that two sides of the coin. So for OR, we have switches in parallel. Those switches are drawn this way: switch 1, switch 2, they are in parallel because current could either flow through here or through here. So only one of them needs to be on for the light to turn on. If both of them are on, that's a very good situation. That means we are definitely going to have current flow uh, through either path. Um, The logic expression in this case is going to be x1. That plus sign indicates OR function. Yes, we do have XOR function. I'm going to talk about that in a few minutes. For OR function, we are going to use a plus sign to represent the OR function, as we used the product sign or the dot to represent AND function. The symbol is going to be slightly different. Now you have a triangle, which is sort of the buffer symbol, but instead of a perfect triangle, we have an arc on the input side. So that signifies an OR symbol. In this case, you have a two input situation going on, but you could also have a three input or a four input OR gate. We are just essentially padding more and more switches in parallel in our circuit model. Okay, so that's about the OR function. Um, how about the NAND function? NAND is, this was and this was not. Bubble signifies inversion. So if you perform an AND function first and then you perform a NOT function, that is the same as NAND or NOT of AND. So we essentially take all the entries in our and complement them. So for example, how do I look at it in terms of a truth table? So if I look back to the truth table of the AND function, I had my inputs are going to remain as is, right? 0, 0, 0, 1, 1, 0, 1, 1. So that's going to remain the same. So if I just monitor the output of and I compare it to the NAND function, I have low, 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 high. And if I look back at NAND, I have exactly the opposite, high, 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 low. So this is essentially the complement or the inverted version of the AND function. So how do I think about the circuit model in this case? Well, I need AND functionality, which means I need switches to be in series, and I need NOT functionality, which means I need the switch to be in parallel with the light bulb. That's the scheme that I used to build a NOT gate. So switches should be in series, switches should be in parallel with the light bulb. Well, if I combine those two concepts or ideas, I have a NAND model in which switches X1, X2 are in series. However, the position of the switches is no longer in series with the light bulb. Instead, it's in parallel with the light bulb. So only when switches X1 and X2 are both closed or on, only then the current will flow through those switches and the light bulb will be off. So that's going to be our NAND function. We still have switches in series, just their location has changed. How do we represent that using an expression? Well, we have X1 and X2, and then because we are complementing or inverting the output, we are just going to use that bar sign to represent that inversion. So X1, X2, and a bar over both of them. That's going to be the logic expression to express the output Y. Can I have more than two inputs for a NAND function? Absolutely yes. I can have two input, three input, four input NAND gates, which means that I'm essentially going to be connecting more and more switches in series. All of those switches are still in this particular path, but I can keep adding switches here. So that's NAND functionality. Next, we are going to look at NOR functionality. The idea is the same. For OR, I needed switches in parallel. So I still have switches that are in parallel. But the set of switches that are in parallel are now in parallel with the light bulb because I need a NOT functionality. So switches are still in parallel, but their location has changed compared to the OR function. The truth table, exactly the opposite of OR. So earlier we had 0, 1, 1, 1, that was for OR. In this case, we now have 1 0 0 0 for NOR. Logic expression, this is going to be OR, and a bar over that is going to make it NOR. Symbol, OR gate, followed by the bubble, which signifies the inversion. So we've got OR followed by NOT. That's going to be our NOR symbol. And as usual, we can have more switches in as at the input. Now you might wonder, how many inputs can I possibly have? Well, there is a limitation on that. So that limitation is called fan in limit. Remember, our voltages have a range to signify low and high states. So I will have to worry about how many inputs I can connect to the input side. I actually have to worry also about how many things I can connect to the output of any logic gate, which is called the fan out limit. So note that there will be some limitation. We cannot have n number or infinite number of inputs, or we cannot connect this output to many things, because we will be playing very dangerously with those logic levels, the range of voltages that signify the logic levels. So there will be limitations on these. But two or even four inputs are perfectly fine for the cases that we are going to see. Okay, let's move on to the exclusive OR function. So student has this on the chat. Let's talk about that function right now. Exclusive or XOR, the truth table is going to be, you have x1 and x2, four possible combinations, 0 0 all the way to 1 1, and the exclusive OR symbol is still the plus sign, but there is a circle over the plus sign, which signifies exclusivity. And the only difference between OR and exclusive OR is, for OR we had 0 here, 1 here, 1 here, 1 here. Now because it's exclusive, when both inputs are on, the output is actually off. So the exclusive OR gate, the symbol is this: OR symbol, but there is an additional arc in the input side. This is x1, x2, and y, and this is my exclusive OR symbol. Exclusive OR gate is also called as the equality detector, because if you can see here, for these two rows, when x1 and x2 are different, it is detecting the output to be a 1. So we can use an exclusive OR gate to detect inequality between the inputs. What is the logic expression? Well, if you can see, when is the output 1? When is, say this is y. When is the output 1? Well, the output is 1 when x1 is 0 and x2 is 1, which is, so let me do this. Let me highlight these entries in two different colors. So I've got blue and yellow to represent the two possibilities. For blue, as you can see, I have x1 to be 0 and x2 to be 1, and the other way around for the next combination. So the output y, which is over here, if I wanted to write an expression for this, I would need to look at where all do I have the ones. I have the ones in two locations, and y can be 1 when x1 is 0 and x2 is 1, and that is represented using this particular term, or x1 is 1 and x2 is 0, which is this particular term. and I have an OR in the middle. And these two are AND operations. And the bar is, of course, the NOT functionality. So that is a quick view at the exclusive OR logic gate. Um, it it looks like we are going to need a few logic gates to build the exclusive OR. We are going to need two AND gates, uh, two NOT gates, and we are going to need an OR gate to to build the exclusive OR. So let's actually go through it. Let's actually draw it out. Say I have x1 here input, x2 here input. I need to invert both of them because I need x1 complement or x1 bar. So let me use two inverters first. Followed by I need to use AND gates, two of them. The inputs to the AND gates are, say for example, for the first term in yellow, I have x1. So I have x1 going into the AND gate and x2 complement. And the output is over here. And for the next term, I have x1 complement. So that guy comes down here. So whenever I want a junction, I'm making a circle. So I'm placing a dot. And when I have a crossover, I'm not. And then for the next term, I also have x2. And the outputs of the AND gate will feed in to an OR function. So that's our exclusive OR logic gate. The output over here as well. All right. Questions so far about exclusive OR and the sort of things we have been talking about. What do we use these circuits for? We are going to use these circuits for building digital devices. So this is going to lead us into a timing signal, which is very useful in a lot of digital circuitry. So things with high and low levels are uh, everywhere, and nothing really is analog anymore. Everything is sort of digital because it has so many advantages. So these are the building blocks to any digital circuit. Okay. If there are no questions, I'm going to move on to one additional gate. So what I'll do is I will try to copy all of this and let's take a look at another gate. Um, this will be our last logic gate. It is going to be exclusive NOR. So we have exclusive NOR here, and because we have NOR, we need a bubble right there. This is going to be an equality detector. Everything is going to flip, which means that instead of these, I'm going to have 1, 0, 0, 1. My logic expression is going to need a bar over it because I'm flipping the output. What else is going to change? Oh, my logic expression is going to change. So let me erase all of this out because it's going to be different. Now I get a 1 when they are both the same, equality detector. So in this case, it should be that expression. So when both of them are 1, so that entry is because of that entry, or maybe I show this one. And that last entry is because of the last entry in the table, the first entry in the table, when both of them are 0. And using the logic expression, you can probably sketch the, the logic diagram or the circuit diagram. So let's see, you're going to have 2 AND gates again. You're going to have 1 OR gate. These are going to feed here. We still need 2 NOT gates. We have x1, x2. x1 goes through, x2 goes through, x2 complement goes here, and this goes here. So that's how we build x1 exclusive OR, x2, and then NOT. Yes, the circle is still there. So first we do exclusive OR, and then we flip it. Okay. Oh no, it's not the same as before. You see, earlier we didn't have the, you see over here, the bar is on the different x1, x2 complement. Over here, we have x1 and x2. Yes, the circle and the plus, that is the same as before. However, now we have a bar over the entire thing, which we did not earlier. Yes. All right. Other questions, guys? Okay. Now we are getting to the meat of our conversation. So far we have been talking about switches and logic gates. Now we are going to bring in the transistor into all of this. So let's take a 5-minute break and let's come back. Right now it is 8:55. We will reconvene at 9 o'clock. So let's just take a quick break and come back. So I'm going to stop the recording, but I will have the WebEx session open. But we'll start talking about again in a few minutes.